In today's video, I'm going to go through your Unit 6 review on techniques of integration. So all of this is deciding which of our strategies we're going to use to integrate. And a lot of these problems are going to look very, very similar, but where you need to use different techniques based on the structure of the problem. So like these first two here, we involve a sine x and an x squared. The first one is a composition where I have an inside function, an outside function, and the inside function's derivative. So we'll do a u substitution. So du is going to be 2x dx. So we'll sneak in a 2, which means we need a 1/2. So this is now sine of u du. Integral of sine is negative cosine. And then plug back in our x squared. Okay, versus the second one, which is a product. And when we have a product, we use integration by parts. You can do this using the uv minus v du or using our tabular method, which will make sense in this case because we're going to have to do multiple integrations. So this is x squared, 2x, 2, and 0. My dv is going to be sine of x, and then we'll integrate. So that's going to be a negative cosine of x, negative sine x, positive cosine of x. Do our diagonals. Alternate the signs. Okay, and then we integrate. So we're going to have negative x squared cosine x plus 2x sine x plus 2 cosine of x, and then we integrate across the bottom, but that's just going to be 0. So we have plus c. Right, these next two again are similar. I'm going to let u equal the square root of x. So du is 1 over 2 root x dx, which we kind of have. So I'll put a 2 here, which is really a 1/2. So then we're going to multiply by 2. So now we just have the integral of cosine of u du. Integral of cosine is sine. So this is 2 sine root x plus c. The second one, I am still going to do the square root. Okay, but in this case, I don't have this in the problem. But with this root, x is u, so this is really 2u over 1, 2u dx. So we can multiply over 2u du equals dx. And this is a strategy that comes when we use square roots. So this is now the integral of 2u cosine u du. So we replace the dx with 2u du and replace the square root with u. This is now a product, so we're going to have to do integration by parts. So my u is going to be 2u, and my dv is cosine u. So this is 2 and 0. Integral of cosine is sine. Integral of sine is negative cosine. So this becomes 2u sine u minus 2 cosine u plus c. And then all of my u's become square roots. So 2 root x sine root x minus 2 cosine root x plus c. In this problem, the first thing I'm going to do, whenever logs are involved, you want to look at, can we simplify using properties? When we have this squared, that's the same as 3 ln of x. And we're going to do a u substitution, because if I let u equal ln of x, du is 1 over x. So this is just 3 times the integral of u du. So that's 3 times 1/2 u squared. So we have 3 halves instead of u. It's really natural log of u squared plus c. Now, just to emphasize the difference, if the whole thing is squared, I can't bring that down. But if it's just the variable, then we can. This one, we again have a product. Our mnemonic for deciding u is log poets. We use logs to help us out. Because the derivative of log is 1 over x. The integral here is going to be 1/4 x to the 4th. So this is plus and minus. So this is going to be 1/4 x to the 4th times the natural log of x minus, I'm going to pull the 1/4 out, the integral of 1 over x times x to the 4th. So the reason we like logs to be our u is that now that's going to simplify to x cubed. So this will be 1/4 times 1/4 x to the 4th plus c. So if you wanted to do it in one more step and make that 16ths, you can. Next we have trig powers. So remembering the derivatives will help you pick which your u should be. Here I've got a composition, so I'm going to let u equal cosine 2x, which means du is -2 sine 2x when we do the chain rule. So I need a -2 in here, which means I'm going to have a -1/2 here. So now this is the integral of -1/2. The cosine 2x cubed is now u cubed. The sine 2x with the -2 is du. So this is -1/8 cosine to the 4th 2x plus t. In the next one, we know the derivative of cotangent is cosecant squared, negative cosecant squared. So I'm going to let u equal cotangent, which means du is negative cosecant squared. So if I'm going to put a negative here, I need the negative here. So this is going to be -1/3 u cubed plus c. 1/3, sorry, this should have just been cotangent. Cotangent cubed x plus c. Alright, so on this next page we have 1 over x squared plus 4, x over x squared plus 4, x squared over x squared plus 4, and then 1 over x squared minus 4. All of these are going to have different strategies. If it's just a 1 over x squared plus something, then that's tangent inverse, and it's always going to be the square root of this. So this is 1/2 tangent inverse of x over 2 plus c. On the next one, I can do a u substitution, because the derivative of that denominator is sort of here. Let's make that 2, 1/2. This is 1/2 the integral of du over u, which is 1/2 ln u. So we have 1/2 ln x squared plus 4 plus c. In this next one, when the degrees are the same, we need to use long division to simplify it. So we're going to take x squared and divide it by x squared plus 4. So 1, and then multiply down x squared plus 4. Then subtract, so we get negative 4. So we have a remainder of minus 4 over x squared plus 4. So my new integral is of that, 1 minus 4 over x squared plus 4. So the integral of 1 is going to be x. Then minus 4 times the integral of 1 over x squared plus 4, which we already did, is 1/2 tangent inverse of x over 2, plus c. So you can leave it like that or simplify it like that. The last one, we can factor this. So if we can factor this, then we want to use partial fractions. So we're going to do some algebra, which makes this x plus 2, x minus 2. So we'll rewrite this as a over x plus 2 plus b over x minus 2. So 1 equals a times x plus 2 plus b, a minus x plus 2, because we want to get our common denominator, so we want to multiply this by x minus 2 over x minus 2, this by x plus 2 over x plus 2, and then pick our values of 2. So if I let it equal positive 2, this one goes away. So b equals 1/4, when x equals negative 2, 1 equals a times negative 2 minus 2, which is a negative 4, so a equals negative 1/4. So we replace that here, and integrate. So those are our integrals. So this will be negative 1/4 ln x plus 2 plus 1/4 ln x minus 2 plus c. So in our next set of problems, again, they look pretty similar. This one, we don't have a 2x or an x, so I can't do u substitution. This can't factor, so we can't do partial fractions. So one of our techniques that's pretty low down on the list but still comes up is completing the square. So we're going to be adding something here, so I need to subtract that same thing so that so we're changing what it looks like but not what it is. So we divide this by 2 and square it, or just think about what makes this a perfect square trinomial. So I'm going to add 1 and subtract 1. So this makes this x squared plus 2x plus 1 is really x plus 1 squared, and then 5 minus 1 is 4. So you can do a u substitution to make this a little bit easier to look at, or you can just do it. So I can rewrite this as 1 over u squared plus 4, which we've already done several times. So this is 1/2 tangent inverse x over 2, or u over 2. So this will be 1/2 tangent inverse of x plus 1 over 2. The next one, we can do a u substitution because of this numerator. So du is 4x plus 1. So because that derivative is here, we can rewrite this as du over u. So that'll be natural log of u, which is going to be natural log 2x squared plus x minus 3 plus c. The next one, unfortunately, that derivative is not there. But we can factor. So this one's going to be partial fractions. Okay, so we can factor this to 2x plus 3 and x minus 1. Because if we FOIL, we get 2x squared minus 2 plus 3 gives me that 2 and then negative 1 times 3. Okay, so I'm going to go off to the side and do that math. So 3x minus 4 over 2x plus 3, x minus 1, is equal to a over 2x plus 3 plus b over x minus 1. So 3x plus 4 equals a times x minus 1 plus b times 2x plus 3. Then we pick our values of x. So if I let x equal 1, then we have 3 times 1 plus 4 is 7. That goes away. B times 2 times 1 plus 3 is 5. Okay, copied that down wrong. This is a minus. So this is 3 minus 4 is negative 1. So B is a negative 1/5. The thing that makes that 0, if we subtract 2, or subtract 3 and divide by 2, is negative 3/2. So when we plug that in, 3 times negative 3/2 minus 4 equals a times negative 3/2 minus 1. So we'll have negative 9/2 minus 8/2 equals a. Negative 3/2 minus 2/2 would be negative 5/2. So negative 17/2 equals a times negative 5/2. So if we multiply by the reciprocal, we end up with 17/5, which isn't all that pretty, but it's fine. So we'll take these two values and plug it in for our a and b. So our new problem is now a, which is 17/5 over 2x plus 3 plus negative 1/5 over x minus 1, and then integrate those. So we'll have 17/5. This 2 means I'm going to need to multiply by a 1/2, and then minus 1/5 ln x minus 1 plus c. Okay, this again looks very similar, but we have different strategies. This one without the x is going to be a tangent inverse. I'm going to let u equal 2x, which means du is 2 dx. So I'll put in a 2 and a 1/2. So this is 1/2 times the integral of du over the square root of 1 minus u squared. That's going to be 1/2 sine inverse of u. Then replace our 2x. This next one I'm going to do a u substitution as well, but I'm going to let it equal the entire radical there. So 1 minus 4x squared, which means du is negative 8x dx. So this guy gets a negative 8, which means we have a negative 1/8 on the outside. Okay, and I'm going to actually rewrite this one more time before I integrate it. I'm going to split this up and put a 2 with that root u, because now I can see that that is the square root of u. So this is negative 1/4 times the square root of 1 minus 4x squared plus c. Okay, these next couple, again, look similar. This one I can split up into 2 integrals because we just have a single thing in the denominator. So I can make this x over the square root of x, which I'm going to write as x to the 1/2 minus 2 over root x. So this one's going to simplify x divided by x to the 1/2. We'd have 1 minus 1/2, which is 1/2. So this is x to the 1/2. I'll go ahead and split these up. Okay. So I'm actually going to do one more step before I integrate. Just like on the last one, now make this a 4, so I can get a 1/2 on the inside there. Alright, so now I can integrate. This one's just going to be the power rule, so I'm going to add 1 to the power, so that's going to make it 3/2. So we need to multiply by the reciprocal. And then here we're going to have 4 root x plus c. The next one I can't split. In this next one, we can't split it up like that because there's nothing we do. But we know radicals lead us to some interesting things. So I'm going to let u equal x squared minus 2. So du is 1 over 2 root x minus 2 dx. That's u, so I can make this 2u du equals dx. So looking back at my problem, I've dealt with that can be u. This is going to be 2u du, but I still have an x remaining. So I need to get that in terms of u. So x is going to equal u squared plus 2. And we're going to make these replacements and hope this helps us out. So in the numerator we have u squared plus 2. This is now u times 2u du. The u here and here cancel. So we're going to have the integral of 2u squared plus 4. So that'll be 2/3 u cubed plus 4u. And then make our replacement back in. Like so. Alright, again, these next 3 all look pretty similar. These 2 are the same with different limits of integration. This one has an x on the outside. So this first one, because we have that x, we can do a u substitution. This one's a definite integral. So when we have a definite integral, we want to change the limits of integration. So I plug in 1, we get 24. I plug in negative 2, that's 25 minus 4 is 21. du is going to be negative 2x dx. So you can make a negative 2 here. So we have a negative 1/2 there. So this is negative 1/2. My new limits of integration are 21 and 24. And then we have the square root of u, which is the same as u to the 1/2. So this is going to be negative 1/2 times 2/3 u to the 3/2, evaluated from 24 to 21. So negative 1/3 24 to the 3/2 minus 21 to the 3/2, and we're going to leave it just like that. This one, we don't have the x, but this is the formula for a semicircle. Okay, so we want the integral from negative 5 to 5, so it's going to be 1/2 pi r, which is 5 squared, which is this. In number 22, since this is not nice bounds on this graph, you would need to do a trig substitution. We're going to set up this trig substitution without actually solving it. So we're going to make this substitution into this problem. Sine theta, which means dx is 5 cosine theta d theta. Okay. My new limits of integration, we need to plug these in for x. So negative 1 equals 5 sine theta, and solve for theta. So divide by 5 and take the sine inverse. And since that's not a unit circle value, we'll leave it. My other one, 2 equals 5 sine theta. Means our lower bound, or upper bound, is going to be the sine inverse of 2/5. And then we'll make all of our replacements. So my new limits of integration are the integral sine inverse of negative 1/5 to sine inverse of 2/5. 25 minus 5 sine theta squared. And then dx gets replaced with 5 cosine theta. So that's how we do our trig substitution, but we are going to leave it just like that. All right, so in this one, if the integral of sine inverse of dx equals f of x sine inverse of x minus x over 1 minus x squared dx, what is f of x? Well, we know from integration by parts, the integral of u dv is equal to uv minus the integral of v du. So we want to look at what we have. We have a function here and its derivative here, which means u is sine inverse. So dv is dx. Okay, which means v is x. Which makes sense if we look at it, because if we had u, so here's my u, here's my v, here's my du, there's my v. Okay, then improper integrals. We use limits. Then we'll integrate. So this is going to be ln of x evaluated from 1 to b. So we're going to have the limit as b goes to infinity of ln of b minus ln of 1. Ln of 1 is 0, but here as b goes to infinity, this goes to infinity. So we say this diverges. Here. Okay, I'll pull the b out and then rewrite 1 over x squared as just 1 over x squared. The integral of 1 over x squared is negative 1 over x. So we're going to have pi times, I'm going to plug in b, so negative 1 over b minus negative 1 over 1. Well, as b goes to infinity, this is going to go to 0. So we're going to have pi times 1, or just pi. All right, this one on the surface may not look like an improper integral, but in the limits of integration here between 2 and 4, our function has a vertical asymptote. So you can break this up into the integral from 2 to 3. And the integral from 3 to 4. So this would be the limit as we're going to replace this with a value. So I'm going to replace that with b. So it says b goes to 3 from the negative side because it's within going from 2 to 3 of the integral from 2 to b of dx over x minus 3 squared plus this one. So I'm actually just going to deal with this one because if this one diverges, they both diverge. And these have a tendency to do that. So if I integrate this, that's going to be negative 1 over x minus 3, and we're going to evaluate that from 2 to b. Plus, if we need to finish that, we will. So we have negative 1 over b minus 3 minus 1 over minus negative 2 minus 3. Well, as 3 goes to b, this is still a vertical asymptote. So that still goes to infinity, which means this one diverges. Okay, we'll do one more of these. So first I'm going to split this up from negative infinity to 0 of dx over x squared plus 9 plus the integral from 0 to infinity of dx over x squared plus 9. Okay, so we'll replace the lower bound with a, we'll replace the upper bound with b. And then integrate. So this is going to be 1/3 tangent inverse of x over 3. Evaluated from 0 to a. All right, so we're going to have 1/3 times tangent, if I plug in 0, tangent of 0 minus tangent inverse of a over 3. So we need to look at what happens to tangent inverse as we go to negative infinity and positive infinity. So tangent inverse, remember, looks like this. It approaches pi over 2 here and negative pi over 2 here. So as this goes to negative infinity, we're going to have 1/3. Tangent's going to go to 0. Tangent inverse of 0 is 0. As we go to negative infinity, this is going to be negative pi over 2. As we go to infinity, that one's going to be pi over 2 minus 0. So we're going to have 1/3 times pi over 2 is pi over 6. Another pi over 6 makes this 2 pi over 6 or pi over 3. All right, so this last one, if f is a twice differentiable function where g of 4 is 7, and the limit is x goes to infinity of g of x is -3, then what is this integral? Well, if I use my limit as b goes to infinity of the integral from 4 to b of g prime of x, that's going to be the limit as b goes to infinity of g of b minus g of 4. Well, the limit as b goes to infinity of g of b is going to be -3. G of 4 is just 7. So this is -10. So that is your Unit 6 review.